Welcome. Okay, so hi, my name's Owen and I'm the CEO of SLAMcore. Today I'm going to take you through our suite at CES and show you some of the technology we've been working on. So just a quick introduction to the company. SLAMcore was founded 7 years ago with the mission to provide technology which will allow companies to build machines that can truly see the world and understand the space around them. We work in a number of different areas. We provide solutions for the XR space, for industrial robotics, and the consumer robotics space. Because we believe that in the future there will be more and more machines that have spatial intelligence, and they're going to be able to do amazing things which will have a huge and profound positive impact on the way we live. But there's a real challenge at the moment where the only companies who can really make these sort of machines have extremely deep pockets and lots of time. So we're looking to reduce the barrier of entry to smaller companies and mid-sized companies by providing our standardized spatial AI SDK, which allows companies to integrate our core algorithms into their products and create products with spatial intelligence, which are going to quite literally change the world in which we live in. So let's get started. Start first of all with our XR solution. So XR headsets need to be able to know where they are in space. They need to know where they are in the room, so that when you move your head from left to right, the visual images that you see also move left to right. If you turn 180 degrees around, then the virtual world should also turn 180 degrees around. So our software provides that core information to the wider stack to be able to allow you to build a virtual reality or an augmented reality experience. So our technology works on Android. It's designed to integrate with the standards like OpenXR. It's extremely low latency, low jitter, and very accurate and extremely reliable. Even when we're talking about large scale environments, this is accurate even up into warehouse scales. So as we see here, this is just our test environment. We don't build the actual virtual worlds ourselves. We're not a games developer ourselves, but this is just a test environment to make sure that the system is working well. And as you can see, as I move it left and right, it's nice and accurate. It's not jittering. It's not getting lost. Very robust. And we can actually go for a nice walk around our suite, but we can actually go much further than you can with other headsets. So we're going to take it outside. And as we walk down here, it doesn't matter even if there's people around, which is actually something many VR headsets really struggle with. And as I walk all the way down to the end of this corridor, moving around, you can see we're still tracking very accurately the location of where I am. And as I get back to the door and open up, we walk through and you can see we're exactly where we left off. And that's our XR offering. So onto the consumer robotics vertical. For a consumer robot to be able to operate, it needs to be able to do three things. First, it needs to be able to build a map of the room or the house that it's operating in. Second, it needs to be able to position itself accurately within that space. Then third, it needs to be able to plan its path from A to B and avoid any obstacles it may encounter along the way. So this is something we have a full solution for, and a number of our customers right now have actually integrated this into their products. So let's go see it in action. So for this next demo, we'll be using the robot down here. We've just turned it on. It has absolutely no idea of the space it's been turned on in. It's not been scanned in advance. This room is completely new. And what we'll do is quickly just drive the robot around. To make this quicker and easier, I'm just going to manually control the machine, but there's no reason why you couldn't implement your own exploration algorithm to actually do this. But as you can see now, as I drive the machine around the space, you can see on the screen a floor plan starting to emerge. And this floor plan is more than just a floor plan, it's actually a 2D occupancy map. This provides all the information the robot needs to be able to know where it's safe for it to travel. So as I said earlier, the three things this robot needs to do is build a map of the space and localize itself. And once we have a map, we can actually now start to send it autonomously to different places. And obviously this is quite a small space, but there's no reason why this wouldn't work in a much larger space. We have some customers using this in very large environments, including warehouses. So now the robot is planning its path. We're using the ROS2 navigation stack for path planning and obstacle avoidance, but all of the localization and mapping is using our SLAM algorithms. It can also avoid obstacles that it may encounter along the way. So actually, let's put an obstacle in the way of it now. Would you like to stand up and stand in the middle of the room? I'll send the robot to the other side of the room, and it will actually see you using the depth camera on the front of it. And it already has seen you straight away. I told it if you weren't in the way, it would have gone and taken a direct path straight to the other side. But because it's been programmed to avoid any obstacles, it's now taking a much wider path to make sure it doesn't make contact with you. Now, the next thing that's really important for consumer robotics, once you're able to do those three things, is you have to be able to do this on very low-cost, affordable hardware. From a sensor point of view, we've got that covered. We can only need 2 cheap cameras, an inertial sensor, and some form of depth sensor, whether that's TOF, whether that's passive stereo, active stereo, or even the LiDAR. But there is no one perfect hardware solution which will work in all these instances. So another thing that's very important to us is to have flexibility around the hardware that we actually operate on. So if we come over to this next booth, we'll be able to see some of the silicon that we actually support. So we support both x86 and ARM architectures. So here you can see a few of the ARM CPU SoCs that we support. So here's the Mediatek Pumpkin i500, the Qualcomm RB3, the Qualcomm RB5, and the Texas Instruments Jacinto. We also have a version of the system running on the Ambarella CV2 chip, and we are also looking to port other ARM-based SoCs. The key is we can actually run on a very small amount of the actual processor that's on these boards. And when it comes to memory, we are extremely lightweight. We can run on just a few tens or hundreds of megabytes. And on the processor, we only need one ARM core and a DSP, or 2 ARM cores, just the A53s. The demo we showed earlier on the robot was actually running on a Raspberry Pi. So that just goes to show how low we can go. So I'll fire one of these up for you now. So let's choose the Qualcomm RB3. This is a mid-range robotics platform from Qualcomm, and we're using the Intel RealSense, which has 2 cameras, an IMU, and a depth sensor on that. But we are actually very flexible about the hardware sensors that we can use. We have an OAK-D from Luxonis, and we also support other sensors from other companies as well. But as I click start, again, the system has never, as far as it's concerned, has never seen this room before. And it starts to build 2 maps. First is this very lightweight sparse map, which we use for localization. But as I move the camera, you can actually see we're also building this 2.5D map, which is a map that the robot uses for its path planning and navigation. In the previous demo, we actually squashed this down to a 2D map, but the 2.5D map actually provides a richer information. And you can see there, if I went for a walk around this entire room, we'd end up with a floor plan of this entire room. As we zoom out, you can see how it's starting to come together. So these chips could all be running on the robot that we showed you earlier. And this means we're providing options to the customers. So they may not be able to afford certain chips, they may want to reduce the price, or they may want higher performance. What we know for certain is there's no one single hardware that's going to be used on every single robot on the planet. So our software has been designed to be very flexible, very portable. It's not agnostic, because the work is required to make it work on these different chips, but when it's working, then it will work day in, day out. So that's our consumer robotics offering. So now on to industrial robotics. So our industrial offering is very similar to the consumer space. The robots still need to be able to build a map, but this time the map needs to be much larger. It could be indoors, it could be outdoors as well. And we also still need to be able to position these machines within that space to very accurate levels. But because the space is so much larger, the complexity is higher. Then finally, the systems also need to be able to avoid obstacles that they encounter along the way. And in industrial use cases, this is critical because safety is paramount. This is something we cope with well, and we have a number of customers. You can just see a few of them on the screen here. Dozens of customers are now integrating our software into their robots, and we're finding a number of interesting use cases as we interact with this market. So actually one of the most interesting ones we found recently is for the ability to use our software for just tracking the position of forklifts in the factory. Right now it can be very expensive to be able to build the infrastructure in a factory to know where your forklifts are. Or the alternative is quite often just people radioing each other, asking where they are. And that's clearly not very good for operational efficiency. So if you are able to integrate our software onto the forklifts, or even a box which you attach to the forklift, then you'll be able to track the position of those forklifts to very accurate levels to be able to increase the efficiency of the assets you have in the warehouse. So if we come over here, we'll actually start to see how this works in practice. Obviously, it's a much smaller space, but if you can actually see how this works on a smaller scale. So if you'd like to take the remote control here, I'll take the other one. So bearing in mind, this technology isn't to build an autonomous forklift, it's to track manually driven forklifts in the warehouse. And as we start to drive around, you can see up on the screen that the position of the forklifts is accurately tracked over time and space. So please feel free to start driving around, and you can see no matter where you go in this entire area, we will always know where that forklift is. So this next demo will be using our service robot. This is where we'll start to map the world in more than just 2 dimensions. So sometimes a robot needs to be able to understand what's going on in 3 dimensions. Whether it's a drone, it needs to plan its path up and under obstacles, or if we want to build something more similar to a digital twin and build that map in a way which is more understandable to a human. So this next demonstration uses exactly the same sensor. It's running on a Jetson NX, and as I start to move the robot around, you can see we're now starting to build a 3D reconstruction of the demo suite. Now as I complete the circle and start to move the robot, I can start to move the screen, and you can see this is a full 3D model of the space in which we're operating. But this is actually much more than just a 3D digital twin. We've also used our neural networks to in real time label all of the obstacles and all of the objects that the robot has encountered. So you can see there in purple the couch, the chairs in green, and actually yourself there in pink. This allows us to do things like remove the people from the map, because quite often when you're building a map, you don't want to have to clear the entire room. So this means you're able to map a space without asking everyone to leave. Maybe you want to remove the chairs and the couches so that we only have the walls and the floors visible. And this is actually what we call this 3rd level of spatial intelligence, where we have the first is just the sparse point cloud, the second is the kind of 2D or 3D geometry, and the third is actually the semantic understanding of the space. And this is really something we're pioneering here at SLAMcore. This allows robots to behave with more intelligence when they're not just dumb machines trying to avoid obstacles that they encounter, but they actually understand the obstacles and what those objects are. And this is where we already start to bring together all of the components of our SLAM system, our localization, our mapping, and our semantic understanding. So if you look at the screen here, you can actually see the real-time semantic labeling happening. Actually, it's pointing at yourself there, sat on the chair, which is marked in purple. And if you just move your legs now, you can actually see this is a real live feed. Now, I will send the robot over to the corner of the demo suite, and it was doing this all autonomously. It's able to identify obstacles that it encounters along the way and then plan a path around them. So the first thing we'll do is we'll use just a static obstacle. I'm going to put a chair in front of it there. You can see clearly segmented as green. And when I send the robot to the other side of the room, it automatically avoids the chair and plans its path around it. Now, one thing to notice is we put a margin of error to make sure that the robot doesn't make contact with the obstacles it encounters. So for that chair, it was relatively small. But in the industrial world, safety is absolutely paramount, particularly around people. So if you'd like to stand up, we can actually show what happens when the robot sees a person. You can see yourself there in the bottom left, your legs are being segmented out, but actually in the map, you can see there's a much wider blue area, which is the exclusion zone of that the robot means it will not enter that space. So when I send the robot to the other side of the room now, the path that the robot plans is much wider to avoid actually any chances of making contact with a person. So when you combine localization, mapping, and semantic labeling all in a real-time system, you get the most intelligent behavior out of a robot. And this is the type of technology we're starting to roll out with our customers. So that's SLAMcore at CES. Thanks for popping by. If you want to learn more, please head to slamcore.com.